Imagine you're flying a helicopter over the Yamal Peninsula in northwestern Siberia. Below you stretches an endless, flat expanse of frozen ground, dotted with lakes and scrubby vegetation, silent and ancient and seemingly unchanging. Then you see it, a hole. Not a small depression, not a crack in the surface, but a massive, near-perfect cylindrical pit punched into the earth as if something detonated from underneath. The walls drop straight down for tens of meters. The diameter spans the width of a city block, and it simply wasn't there before. No earthquake was reported, no meteor strike was recorded, no human machine carved it out. The frozen ground just opened up, and nobody saw it happen. That's where this story begins. Enormous craters appearing suddenly in one of the most remote and inhospitable landscapes on Earth, with no obvious explanation and no warning whatsoever. The central question isn't just surprising, it's genuinely unsettling. What is exploding out of the permafrost right now? And why? Here's what makes these craters more than just a spectacular geological curiosity. They're appearing in ground that has been frozen solid for thousands of years. Ground that, by every reasonable assumption, should be stable. And the leading explanations for what's driving these explosions pull in some of the most consequential forces shaping our planet right now: extreme pressure, trapped ancient gas, and an Arctic that is warming faster than almost anywhere else on Earth. This isn't just about strange holes in the ground. It's about what those holes might be telling us about processes happening far beneath the surface and far into the future. There's a lot of early speculation surrounding these craters that has since been revised, replaced, or quietly abandoned. Missile tests, aliens, methane bombs of apocalyptic scale. Some of those headlines were hard to resist. What the science actually shows is both more precise and in some ways more interesting than the wilder theories. Over the course of this video, we're going to separate the noise from what researchers have genuinely established and be honest about what still isn't fully understood. Before we get into it, if you're watching this late at night or listening while you drift off, I'd love to know where you are right now and what time it is there. Drop it in the comments. Now let's go to Siberia. The year is 2014. A helicopter pilot flying over the Yamal Peninsula spots something that stops the conversation in the cockpit. He circles back, then circles again. What he's looking at doesn't make sense against the landscape he's flown over hundreds of times. A crater. Not a gradual depression, not a sinkhole with crumbling edges, but a sharp, almost geometric opening in the frozen ground, with walls so clean they look almost deliberate. He photographs it. Those photographs make it to the Russian media, and within days the rest of the world is staring at them too. That first widely documented crater, known as the Yamal crater, or simply B1, became the image that launched 1,000 headlines. And the headlines were spectacular. Giant hole appears in Siberia. Mystery crater baffles scientists. The photographs showed a roughly circular opening that measured somewhere between 20 and 30 meters across, with walls plunging nearly straight down into darkness. Around the rim, chunks of frozen earth had been hurled outward in a pattern that looked less like a collapse and more like an explosion. Something from underneath had pushed up and out with enough force to scatter debris across the surrounding tundra. Here's what made the images so visually striking and why they hit the public imagination so hard. The Yamal Peninsula is flat, brutally, monotonously flat in the way that only the high Arctic can be. It's a landscape that seems to resist drama. Frozen lakes, low grasses, the occasional shrubby willow, and then horizon. Against that uniformity, a perfectly cylindrical pit of unknown depth looks genuinely alien. The eye doesn't know what category to put it in. It doesn't resemble a cave entrance. It doesn't resemble a mining operation. It doesn't look like anything natural, which is exactly why the first instinct for many observers was to assume it wasn't. The earliest guesses came fast and they came wide. A meteor impact was one of the first suggestions floated, which made sense as an instinctive reaction. Impacts leave craters, but the geometry was wrong. Meteor impacts produce shallow, bowl-shaped depressions with raised rims. The Yamal crater had near vertical walls and descended far deeper than any impact of that size would suggest. The physics didn't align. Other theories moved quickly through the information cycle, an underground explosion of some kind, a weapons test, a gas pipeline rupture, though no infrastructure ran beneath that exact location. Some corners of the internet moved directly to the more creative end of the spectrum, and the words UFO and aliens appeared with predictable regularity. These weren't theories that scientists took seriously, but they spread, and they shaped the emotional texture of the story before any researcher had actually stood at the edge of the crater and looked down. What made the scientific response slower than the speculation was simple geography. The Yamal Peninsula is not easy to reach. It sits above the Arctic Circle in western Siberia, accessible primarily by helicopter, and only during windows of weather that aren't always cooperative. The terrain itself is treacherous in ways that aren't immediately obvious from aerial footage. Permafrost ground can look solid and stable until you step on it and discover pockets of saturated soil just beneath the surface. Working at the edge of a crater with unknown internal stability in remote terrain with no quick route to emergency medical care requires preparation that takes time. Scientists couldn't simply drive out and start measuring. They had to plan, equip, and wait for the right seasonal conditions. The first serious fieldwork began relatively quickly given those constraints. Russian researchers from the Center for the Study of the Arctic and other institutions reached the crater site within weeks of its public discovery. What they could verify immediately was straightforward but important. The crater was real and newly formed. Local reindeer herders in the area reported that it had not existed the previous year, meaning the event had occurred sometime in the months before discovery, likely in late 2013 or early 2014. The debris field around the rim confirmed that material had been ejected outward rather than falling inward. Whatever happened, it came from below. What remained speculative at that point was almost everything else. The depth of the crater, the composition of its walls, the precise mechanism that created it, and whether it was a singular anomaly or part of a broader pattern. The initial measurements were rough, and the early photographs, while dramatic, couldn't answer the structural questions that geologists needed answered. The hole was there. The cause was not yet on the table. Then more craters emerged. Within a year of the B1 discovery, at least 2 additional formations had been identified in the same general region of Siberia, one on the Taimyr Peninsula and another in the Yamal area. Suddenly, the isolated anomaly became a pattern, and a pattern demanded a different kind of explanation. Single events can be dismissed or filed away as flukes. Multiple events in similar terrain, appearing within a short time frame, suggest a mechanism. Something was producing these formations, and it was doing so across a significant stretch of Arctic ground. The public mystery had already taken shape before the science could catch up. People were searching for meaning in photographs taken from hundreds of feet in the air, building theories from crater rims and debris fields, without knowing what lay beneath. That gap between first impression and careful investigation is worth holding on to, because it shaped which questions got asked loudly and which ones got asked quietly. Some of the loudest early questions turned out to be the wrong ones, but a few of them, almost accidentally, pointed in exactly the right direction. And what the actual fieldwork eventually uncovered was stranger and more coherent than almost any of the initial guesses. To understand why the ground could open like that in the first place, you have to stop thinking of the Siberian tundra as frozen dirt and start thinking of it as a kind of layered archive. Imagine slicing down through that flat landscape like a piece of cake. At the very top, a thin, fragile skin of soil that thaws each summer and refreezes each winter. Below that, sometimes just a meter down, sometimes dozens of meters, you hit the real Arctic foundation, permafrost. Permafrost isn't just cold soil. It's any ground that stayed at or below freezing for at least 2 consecutive years, often much longer. In much of Yamal and Gydan, that 2 years is more like tens of thousands. During that time, snow has fallen, plants have grown and died, animals have grazed and decayed, rivers have shifted, seas have advanced and retreated. All of that leaves traces. Permafrost locks those traces in place. Frozen into that ground is ice, and not just as tiny crystals between grains of sand. In some layers, the ice forms massive lenses and wedges, pure and clear, thicker than a person is tall. Between and around those lenses sit sediments, ancient roots and mosses, bits of peat, entire pockets of organic mush that never quite finished decomposing because it got buried and frozen instead. That unfinished decomposition matters because when organic matter is trapped away from oxygen, microbes don't stop working. They switch strategies. They begin to produce gases, carbon dioxide, methane, and others. Those gases seep and migrate. Some escape to the atmosphere. Some get trapped in deeper layers or dissolve into groundwater or form strange solid compounds with water molecules called gas hydrates that only remain stable under cold temperatures and pressure. So under that flat tundra, you have more than frozen mud. You have ice, sediment, long-dead plant material, and pockets and pathways for gases, all held in a state that assumes one thing: cold. Now put that archive in a very particular setting. The Yamal and Gydan Peninsulas jut into the Kara Sea like twin fingers. They sit above the Arctic Circle, built on old marine sediments, shaped by glaciers and the sea, and riddled with relics of past climates. Permafrost there can reach hundreds of meters deep, but it isn't uniform. Some zones are ice-rich, others are comparatively dry, some layers formed on land, others were laid down when this area was seabed, saturated with salt water and organic slurries. On top of that geological patchwork, you have a climate that swings hard between seasons: long, dark, intensely cold winters and short summers that can be surprisingly warm, with standing water pooling in shallow depressions and sunlight lingering almost all night. Those conditions don't just sit still. They breathe, annually. Each year, the thin, active layer at the surface thaws and softens, sometimes only a few tens of centimeters, sometimes more than a meter. Plants grow, water moves, gases exchange. Then winter clamps down. The active layer refreezes and welds itself back onto the permafrost beneath. Over decades and centuries, those freeze-thaw cycles gently remodel the landscape. They puff the ground up here, crack it there, drain one pond, create another. Stability in this context doesn't mean nothing moves. It means things move slowly and predictably. Now start changing the rules of that seasonal game. In the past few decades, average temperatures in the Siberian Arctic have risen much faster than the global mean. Summers are warmer. Thawing goes deeper. The ground doesn't cool as thoroughly in winter as it once did. Snow can arrive later, and paradoxically, thicker snowpacks can act as an insulating blanket, keeping the ground beneath warmer than bare, exposed soil would be. All of this adds up to a permafrost system under increasing stress. When that stress builds, the landscape can fail in different ways. In many places, thawing ice simply melts, turning hard, frozen ground into soggy, unstable muck. The surface slumps. Lakes expand as their shorelines crumble. That's the slow-motion version, dramatic from space but not explosive. But permafrost can also store pressure. Picture a lens of nearly pure ground ice buried beneath a layer that warms from above. Meltwater forms and has nowhere to go because the underlying layers are still frozen and impermeable. Or imagine a pocket of gas-rich sediments overlain by an icy, solid cap. As temperatures nudge upward, microbes become more active in buried organic material. More methane and carbon dioxide are produced. At the same time, warming can destabilize gas hydrates, releasing additional methane that was previously locked in solid form. Those gases migrate upward until they encounter a barrier, a dense frozen layer with low permeability. The more gas accumulates beneath that cap, the more pressure builds. The surface doesn't advertise all of this clearly, but it sometimes whispers. One way it does that is through features called pingos, ice-cored hills that rise slowly as groundwater freezes and expands beneath them. To an untrained eye, they're just low, rounded bumps on the tundra. To a geocryologist, they're clues about what's happening underground. Traditional pingos grow over centuries. They may crack at the top, drain slowly, and collapse into circular ponds. In parts of Yamal and Gydan, though, researchers began noticing something a bit different even before the famous craters drew global attention. Small bulges and domes of ground that seemed unusually steep, sometimes associated with wetter soils and subtle cracks. Local reindeer herders reported mounds that hadn't been there a few years before. In some cases, the pressure inside these features was high enough that drilling or sampling released abrupt bursts of gas. Not all of these mounds are destined to explode, but they hint at zones where ice, water, sediment and gas are interacting in unstable ways. Methane sits at the centre of this story, not just because it's flammable, but because of how it behaves underground. It's generated by microbes chewing through waterlogged organic matter, and by the breakdown of deeper thermogenic sources tied to ancient hydrocarbons. It can move slowly through pores in the soil, dissolve into groundwater, or collect in discrete pockets. It's lighter than water, so it tends to rise, but if it encounters a frozen lid that's strong enough to hold, it can accumulate to surprisingly high pressures. As long as that lid stays cold and thick, it can contain the system. Start thinning and warming it from above, and you increase the odds that it will deform, crack, or fail. That's the background against which those sudden Siberian craters started to look less like miracles and more like extreme endpoints of a continuum of permafrost behaviour. Researchers who had been patiently mapping thaw slumps, subsiding coasts, and shifting lakes now had another category to add: rapid, localised blowouts where stored gas and destabilising ice combined to rearrange the surface in a matter of seconds. The warming trend doesn't guarantee more explosions. The Arctic is vast, and many permafrost regions may continue to thaw in slow, messy, non-explosive ways. But that trend changes the odds and focuses scientific attention. Features that might once have been dismissed as just another bump in a remote tundra field are now monitored, photographed, sometimes even instrumented. Because if you want to explain a hole that shouldn't exist, the first step is recognizing that, underground, the conditions for sudden failure have been building for a long time. With that buried context in mind, we can return to the craters themselves and look not just at their shape, but at what their exposed walls and floors revealed about the events that formed them. When the first teams finally reached these new craters, they weren't walking up to tidy geological specimens, waiting patiently for inspection. They were stepping into active, changing systems that did not particularly want to be studied. To even get there, scientists had to borrow some of the same skills as the reindeer herders and gas workers who reported the holes in the first place. Helicopters when the budget allowed, all-terrain vehicles and snowmobiles when it didn't. Sometimes days of travel over boggy tundra, rivers that hadn't quite frozen enough, or ice that might have started to rot from beneath. They carried sampling gear, gas analyzers, corers, drones, and increasingly a kind of quiet awareness that the ground under their feet might not be as solid as it looked. The danger wasn't abstract. A crater that opens one summer can have an unstable rim the next. The overhanging edges are cut into ice-rich permafrost, already under thermal stress. One misstep on a thawing ledge, one block of ice detaching without warning, and a researcher could find themselves sliding into a steep, slick bowl, tens of meters deep, with no easy way out. Add to that the possibility of gas still venting from the newly exposed walls, and you have a field site that behaves more like an industrial accident scene than a tranquil research pit. Because of that, the first pass at many craters came from the air. Drones became the new field assistants. Researchers launched them from safer, more stable ground, sending them buzzing out over yawning cavities that, from above, looked almost impossibly clean. They mapped the craters in fine detail, capturing high-resolution images and building 3D models that could be rotated and analysed back in the lab. From those models, some things became immediately clear. These were not ragged, slumping sinkholes. The fresh craters, the ones documented within a year or two of formation, were sharply defined and almost unnervingly geometric. Steep, near-cylindrical walls dropped straight down 20, 30, sometimes more than 40 metres. The openings were often close to circular, with diameters on the order of tens of metres. though some widened and became more irregular as they aged. Around many of them, the tundra told its own version of the story. A ring of displaced debris circled the rim, blocks of frozen soil and massive chunks of clear, blue-white ground ice hurled outward and then frozen in place where they landed. Some pieces lay dozens of meters from the edge, angled as though they'd been thrown rather than gently pushed aside. In a few cases, the explosion had cut through the overlying vegetation like a cookie cutter, leaving near-vertical slices of moss and sedge turf still draped over the lip. Inside the craters, the exposed walls were a cross-section of permafrost history. Bands of icy sediment, layers of older peat, lenses of almost pure ice. Stratigraphy that, until the blowout, had been locked away from direct observation. Scientists rappelled down when it was safe enough, hammered out frozen cores and measured temperatures at different depths. They traced the contacts between layers, looking for signs of former lake beds, old marine deposits, or buried ice wedges. Gas measurements were the other crucial piece. In some craters, especially those reached soon after formation, methane concentrations in the air near the bottom were far above background. In a few, researchers could see bubbles still escaping from the floor, where meltwater and mud pooled over deeper sediments. By sampling those gases and analysing their isotopic signatures, they could ask, is this methane mainly biogenic, produced by microbes chewing on ancient plant material? Or is it thermogenic, leaking upward from much deeper hydrocarbon reservoirs? The answers were mixed, but informative. Many samples bore the light, microbially derived fingerprints of permafrost and shallow sediment methane. Others showed a component that looked more like deeper thermogenic gas, hinting at contributions from underlying petroleum systems. That combination didn't solve the mystery outright, but it narrowed the possibilities. It suggested you weren't just dealing with a simple swamp gas burp or a pure pipeline leak. You were looking at a complex system where multiple sources could converge beneath a frozen cap. Soil and sediment samples added additional constraints. By analysing grain sizes, ice content, and the orientation of crystals in ice lenses, geocryologists could reconstruct aspects of the pre-explosion environment. Some craters cut through what used to be lake or bog basins that had filled in and refrozen. Others punctured uplifted mounds, those suspicious bulges that locals had started to notice, confirming that at least some of the explosions were the final failure stage of pressurized bubbles in the ground. But timing was everything, and it rarely worked in scientists' favor. The Arctic doesn't pause while we catch up. In the first few months after a blowout, a crater might have bare vertical ice walls and a visible floor. By the next warm season, meltwater can begin to cascade in, thawing and eroding the sides. Blocks slump, the shape softens. Within a couple of years, many craters start to fill with water, from rain, snow melt, and groundwater seepage. They transition into deep, steep-sided lakes, visually indistinguishable from older thermokarst ponds unless you know their history. Arrive too late, and the crucial evidence of an explosive origin is partly erased. The clean blast pattern on the surrounding tundra gets overgrown. Melt blurs the crisp stratigraphic exposures. Gas pressures have already vented. You're left reading a crime scene that nature has been quietly tidying away. That is why repeat observations became so important. As more craters were detected, by gas workers in helicopters, by herders on migration routes, by satellites that suddenly noticed dark circles where bright tundra had been the previous year, scientists could compare. A fresh crater with standing icy walls here, a 2-year-old crater already half filled with water there. A decade-old feature that now looks like just another lake. Patterns emerged. The consistent presence of ejected material around the rims argued strongly for an explosive or at least very rapid venting event, not a slow-thaw slump. The nearly vertical walls and clear stratigraphy implied that the ground had been solid and ice-rich right up until failure. The gas signatures, combined with the known geology of Yamal and Gydan, pointed toward methane playing a central role, though not always from the same depth or source in every case. At the same time, the growing catalogue of sites highlighted just how incomplete our picture still is. Many explosions almost certainly go unobserved, especially in more remote regions. By the time a satellite pass or a field team happens to notice a new depression, the immediate post-event window is gone. Instrumented before and after records, ground temperatures, pore pressures, gas fluxes are almost non-existent because we don't yet know exactly which hummock of tundra is going to blow. In other words, most of our data are forensic, not predictive. We're excellent at reading the scars after the fact, less so at watching the wound open in real time. That's enough to rule out some early ideas like meteorite impacts or human explosives in every case, and to build a strong circumstantial case for gas-driven blowouts in ice-rich permafrost. But it still leaves room for debate about the exact trigger mechanisms, the relative contribution of shallow versus deep methane, and why some stressed mounds fail quietly while others detonate. To move from "this is probably what happened" to "this is how it happens" step by step, researchers had to take the next logical step, connect the physical evidence at the crater sites to a specific process that could store, concentrate, and suddenly release enough energy to reshape the ground in seconds. That's where the leading explanation, part methane reservoir, part permafrost volcano, began to take shape. Imagine the ground under your boots is not really ground, but the frozen lid of a pressure cooker. From the surface, it looks like ordinary tundra, a sponge of moss and sedges, maybe a few dwarf shrubs, lying over what seems like solid, eternally frozen soil. But a metre or two down, things are not simple at all. You have layers of ice-rich sediment, old lake beds, buried peat, and in many places, pockets and veins of gas-charged material that have been trapped there for thousands of years. Now picture this. As the climate warms, as summers lengthen, and heat penetrates just a little deeper each year, that layered system begins to rearrange itself. Water seeps into old thawed zones and refreezes. Ice lenses grow and push upward. Methane that was comfortably locked in ice or dissolved in pore water finds itself in a slightly warmer, less stable environment. In some locations, deeper gas from underlying reservoirs also migrates upward along fractures and faults, searching for any pathway toward lower pressure. If the overlying permafrost is thick and cold enough, it can act like a cap rock in a petroleum system, a tight frozen seal. Gas moving up from below hits that barrier and starts to collect beneath it, in the same way steam accumulates under the lid of a pot. The key is that unlike liquid water, methane is compressible. As more molecules squeeze into the same space, the pressure goes up. This is the core of the leading hypothesis. You have a sealed, ice-rich roof. Below it, a zone where gas and water and thawing sediments can move. Over time, methane accumulates. The ice in the overburden may even help by deforming plastically, bulging upward as pressure below increases, instead of cracking early and venting the gas harmlessly. On the surface, that process can express itself as a gentle dome, a swelling mound where the tundra grass looks a little higher, a little more arched than the terrain around it. Locals and scientists have given these features different names, but the concept is familiar in cold regions geology. A pingo. Classic pingos are hills formed when pressurized groundwater freezes and expands, slowly heaving the ground into a frozen blister. They tend to grow over decades or centuries and fail more or less quietly when their icy core thaws and collapses. You're left with a sagging depression or a small lake. What's happening in these Siberian explosion craters seems to be a more volatile cousin of that process. Some researchers call them gas-charged pingos or pingo-like mounds, because the shape is similar, a bulge with an ice-rich interior. But instead of water pressure alone, you have a mix of ice, water, and pressurized methane doing the pushing. As temperature and pressure conditions evolve, the integrity of the frozen cap is tested. The mound may grow over several years, imperceptibly at first, then more clearly. Meanwhile, gas keeps feeding into the pocket beneath. The pressure keeps climbing. At some critical point, the stress on the overlying permafrost exceeds its strength. Ice bonds fracture. Frozen soil, that concrete-like mixture of mineral grains and interlocking ice, fails not by gently sagging, but by snapping. When that happens, all of the overpressure is released in a burst. Gas expanding from high pressure to low does mechanical work on the overlying material. It shoves it aside, accelerates it upward and outward. The result is what field teams later see: blocks of frozen ground, some the size of cars, thrown tens of meters, turf peeled back and draped over the rim, a clean, cylindrical void where solid ground existed moments before. Because this involves a phase change-prone substance, methane within ice, stored pressure, and an eruption through a frozen crust, some scientists have reached for a striking analogy: cryovolcanism. On icy worlds like Enceladus or Europa, cryovolcanoes don't spew molten rock. They vent water, ammonia, or other volatiles through an ice shell. The physics is not identical. Siberia is not Saturn's moon, but the pattern is reminiscent. You have a cold, brittle lid. You have volatile, rich material underneath. You have gradual pressure build-up, then a sudden rupture, and an explosive release. In that sense, these Arctic blowouts behave like tiny permafrost volcanoes, cryovolcanic-like events driven not by magma, but by gas and thawing ground ice. Methane is central because it plays multiple roles in this story. First, it's a potent gas that can be stored in different forms, as free gas in pore spaces, dissolved in water, or locked into ice as clathrate-like structures. Changes in temperature, salinity, or pressure can move methane between those forms, altering how much can be crammed into a given volume before pressure spikes. Second, methane has both shallow and deep origins in these regions. Microbes digesting ancient organic matter in thawed sediments produce biogenic methane. Deeper in the subsurface, high heat and pressure crack buried organic material into thermogenic gas. Faults, old river channels, and thawed zones in permafrost can connect these worlds. So the pocket beneath a mound may be fed from above by microbial gas, from below by migrating thermogenic gas, or both. Finally, methane is light and buoyant. Given any weakness in its overburden, it wants to move up, concentrating against the coldest, most impermeable layer it encounters. In much of Yamal and Gydan, that layer is the intact permafrost cap near the surface. That's how you end up with a shallow high-pressure zone rather than a diffuse, harmless seep. The reason this model has become the leading explanation is that it matches the physical evidence in ways many early ideas did not. Meteorites would leave impact signatures in the sediment, and often fragments; those are absent. Man-made explosives would produce different chemical residues and blast geometries, and they don't appear in most cases. Slow thaw slumps and subsidence can create lakes and depressions, but they don't throw coherent blocks of frozen soil outward in radial patterns. The gas-charged Pingo blowout model, on the other hand, accounts for the nearly vertical walls, consistent with a sudden removal of support rather than slow erosion. It explains the raised rims of ejected material and the distance large blocks have travelled. It fits with drone-mapped crater shapes that are initially close to circular, as you'd expect if the failure propagated in all directions from a pressurized point beneath a roughly uniform cap. It also meshes with the gas data. Elevated methane near the bottoms of fresh craters, isotopic signatures that point to a mix of shallow and deeper sources, and the fact that many craters are located where geological maps show underlying hydrocarbon structures, or old lake basins that could accumulate microbial gas. All of that lines up with the idea of a methane reservoir punching through permafrost. But leading explanation is not the same as closed case. Researchers still debate the details of how the pressure builds to explosive levels. Does the gas accumulate in discrete cavities like a balloon, or within a more diffuse ice-rich matrix that suddenly fractures? How important are gas hydrates, ice structures with methane trapped inside, as a source? Are some mounds mainly pressurized by groundwater freezing, with methane only providing the final kick? What precise combination of warming, hydrology, and gas flux turns one bulging pingo into a quiet collapse and another into a detonation? There are also questions about timing and triggers. Does a particularly hot summer push a stressed mound over the edge? Do heavy rains or rapid snowmelt inject enough water to change pressure conditions abruptly? Could subtle seismic activity fracture the cap at just the wrong moment? The evidence for the general mechanism, gas beneath a frozen seal, pressure build-up, sudden rupture, is now strong. It's consistent across multiple sites and supported by both field observations and numerical models. But the exact choreography of ice, water, and methane in the hours, days and years before an explosion is still being worked out. And in that uncertainty, alternative interpretations and refinements continue to emerge as scientists argue over how many routes there might be to blow a hole in the tundra big enough to swallow a house. If you gather the papers and reports that have come out since the first Yamal crater hit the news, you don't see one clean, single mechanism stamped on every diagram. You see a family resemblance, and then a lot of argument around the edges. One camp leans more heavily on classic thermokarst processes. In that view, the key actor isn't just gas, it's ice. Permafrost in these regions is shot through with massive ground ice, wedges, lenses, buried lake bottoms that are more frozen water than sediment. When those ice bodies thaw, the ground doesn't gently settle. It can collapse catastrophically. Depressions form, slopes fail, ponds appear where there was once dry land. That's thermokarst. Some researchers argue that what we're calling explosion craters are, in a subset of cases, thermokarst features that happen to interact with gas at the right stage. Maybe a buried ice lens starts to melt. The overlying soil sags, cracks propagate downward, and those fractures suddenly connect a shallow gas pocket to the surface. The release might still be violent, but the primary driver is loss of mechanical support as ice disappears, not a pure gas bomb under an intact lid. Others shift the focus deeper. They point to the geology beneath the permafrost, conventional gas fields, old fault zones, ancient river channels now filled with permeable sediments. In that picture, the permafrost is less a self-contained system and more a leaky roof over an active basement. Thermogenic gas from deep reservoirs migrates upward along faults, hits the cold permafrost, and pools. If the flux from below is high enough, you don't need much microbial methane or clathrate breakdown near the surface. The deep system is doing the work, slowly inflating a pressurized zone against the frozen cap until something gives. And then there are hybrid models, which are probably closest to reality. A mound might begin as a fairly ordinary pingo raised by freezing groundwater. Microbial methane in thawed sediments adds some extra pressure. Deep gas trickling up a fracture over decades adds a little more. Progressive thaw weakens the ice-rich core from above, while that mixed gas and water soup pushes from below. The final failure isn't pure thermokarst or pure gas blowout or pure groundwater heave. It's all of them, in different ratios depending on the site. That's one reason why many researchers now warn against assuming every Siberian crater formed in exactly the same way. When you line up the known examples, they're similar but not identical. Some are relatively shallow with broad rims. Others are narrow shafts dropping tens of meters. Some sit over known hydrocarbon structures, others do not. Some were associated with well-documented mound growth in satellite images before failure. Others seem to have appeared more abruptly. It would be surprising if one mechanism, with one set of parameters, accounted for such a range. Then there are the specific questions that refuse to neatly resolve. Trigger timing, for one. Why does a mound fail in August of 1 year instead of August 10 years earlier or 10 years later? Field teams often arrive after the fact, so they're reconstructing a crime scene without security footage. They can see a warm summer in the weather records, or unusual rain, or an early snowmelt season. But those patterns are common across the region. Only a handful of mounds actually explode. The depth and nature of the gas source remain contentious as well. Is most of the methane in a given crater coming from a shallow, thawing peat layer, from gas hydrates decomposing within the permafrost column, from a deep thermogenic reservoir pushing its way up? Isotopic signatures provide clues, but often point to mixtures. Mixtures are messy to interpret. And the role of short-lived weather extremes is still being untangled. Does a freak heatwave soften the upper few meters just enough to change how stresses are distributed in a mound? Do heavy autumn rains saturate a dome, increase pore pressures, and nudge it past a tipping point? Could a winter with sparse snow cover, and thus colder ground, paradoxically strengthen the cap and delay failure? Models suggest all of these might matter, but disentangling their contributions in any single event is difficult. In that vacuum of certainty, more dramatic stories had room to grow. Early on, Some media outlets floated ideas of meteor strikes punching holes in the tundra, or secret weapons tests leaving artfully circular scars. Those explanations are narratively satisfying. One big object from the sky, one big bomb from a lab, one simple cause you can picture instantly. They also tend to leave clear signatures. Meteorites leave high-speed impact deformation, shock minerals, fragments of extraterrestrial rock. High explosives have characteristic residue patterns and blast geometries. Repeated field surveys simply didn't find those fingerprints. Instead, they found ice cores, gas-rich sediments, gradual dome growth in archived satellite images, boring incremental processes leading to a sudden but very earthly failure. Sensational claims gained traction, partly because the first good crater photos were so alien, and partly because the true story is subtle. The idea that invisible gas has been quietly inflating a frozen hill for years, waiting on just the right combination of thaw, rain, and stress to fail, is less cinematic than a fireball from orbit. But it fits the data better. This is what frontier science looks like, especially in a place where field seasons are short, logistics are brutal, and the thing you're studying may blow itself apart without witnesses. Uncertainty here is not a sign that scientists are clueless. It's a sign they're working at the margins of what their instruments, their models, and their access allow. Over a decade, the mystery has narrowed. We're no longer asking, is this a meteor crater or a conspiracy? We're asking, how much deep gas versus shallow gas? Which combinations of ice structure and weather tip a mound into explosion instead of quiet collapse? The broad outline, gas under pressure beneath a fragile frozen cap, has come into focus. The fine print, the choreography of thermokarst, groundwater, hydrates and climate anomalies that determines which patch of tundra will detonate, is still being written. If you live thousands of kilometers away, it's tempting to file these craters under weird Siberian trivia and move on. But the scientists working on them don't have that luxury, because the next question practically asks itself, are there other hills out there quietly inflating toward the same kind of failure? Once people knew what to look for, they started finding it. When researchers went back through old satellite archives of Yamal and Gydan, frame by frame, year by year, they noticed something that hadn't registered before. In several cases, a crater that suddenly appears in a 2014 or 2015 image had been a small, smooth dome in 2012, a slightly taller dome in 2013, a subtly sharper, higher bump in early 2014. If you didn't know that bump would one day explode, you'd probably never give it a second thought. On a satellite image, it's just another pimple on a very lumpy landscape. But in hindsight, you can trace the outline, a mound that rises, steepens, then vanishes into a void rimmed with ejecta. Once that pattern became clear, teams started scanning for similar mounds that haven't failed yet. On the ground, these features can look like oversized pingos or frost-heave hummocks, maybe a few meters high, sometimes more. The vegetation on top is often intact, but the slopes can be unusually steep, with tension cracks, little scarps where chunks have slumped away. In a few cases, ground-penetrating radar has shown chaotic internal structure, ice lenses, gas pockets, unfrozen slurry in odd places. Not your standard well-behaved hill. They're now often called bulging mounds or heaving domes, and some researchers treat them as pre-crater warning signs. That doesn't mean every dome is a time bomb. The Arctic is full of mounds raised by freezing groundwater, subsiding old pingos, thermokarst edges. But a subset shows the right combination of rapid growth, gas anomalies, and unstable ice. Those get flagged. The sheer size of the Arctic makes finding them a remote sensing problem first, and a boots on the tundra problem second. Satellites do the initial sorting. High-resolution commercial imagery, radar instruments that can see through clouds and polar night, laser altimetry that measures surface elevation to within centimeters. These tools can catch a mound that rises 50 centimeters over a few years. That kind of growth used to be invisible noise. Now it's a data product. Researchers run change detection algorithms on enormous image archives, watching for bumps that appear and swell between seasons. Radar backscatter picks up subtle changes in surface roughness and moisture that might hint at thawing ice or gas-charged sediments. Thermal sensors sometimes see warm anomalies in winter, where gas movement or groundwater flow is bleeding heat toward the surface. Then come the aerial surveys. Planes and drones fly low over suspect regions, stitching together fine-scale elevation models, taking repeat passes to see if anything is still moving. You can think of it as a triage step. Out of hundreds of candidate mounds on satellite images, which doesn't actually look worrying from closer up, ground teams are the final, risky layer. They set out across boggy, mosquito-ridden terrain to hammer in gas probes, drill shallow cores, deploy temperature cables. In a few cases, they've recorded methane concentrations, orders of magnitude, above background just centimetres below the surface of a mound. The frozen cap is literally sitting on a cushion of pressurised gas and water. At that point, the question of hazard stops being abstract. Northern Siberia and other permafrost regions aren't empty. There are reindeer herders, small settlements, gas fields, pipelines, winter roads, remote research stations. A spontaneous blowout crater forming 50 kilometres from the nearest camp is mostly a scientific curiosity. The same event under a buried pipeline or close to a village is a different story. The force involved in these blowouts is comparable to a small industrial explosion. They fling blocks of soil and ice dozens of metres, carve deep shafts, destabilise slopes. A field crew unlucky enough to be pitching a tent on a growing mound at the wrong moment would have little chance. Engineers and planners are starting to pay attention. Some pipeline routes and well pads are now checked against permafrost stability maps and known dome clusters. In theory, you can avoid obvious high-risk zones the same way you avoid active landslide scars or floodplains. In practice, the data are patchy, and the ground is changing faster than most infrastructure was designed for. That acceleration is the other part of the story. Even if we don't know exactly how many craters will form in the next 20 or 50 years, we do know the Arctic is warming at roughly 2 to 4 times the global average. Permafrost that once stayed locked solid for millennia is now going through deeper seasonal thaw, more frequent melt-freeze cycles, more thermokarst collapse. Every extra degree of warming pushes the active layer deeper each summer. That changes stress patterns in ice-rich mounds, alters groundwater flow, and can bring previously frozen gas-bearing sediments into play. It doesn't guarantee more explosions at specific spots, but it nudges more of the landscape into the zone where gas charge failure becomes possible. You can think of it like this. The deck is being reshuffled. The total number of explosive craters may stay low compared to, say, the number of thaw slumps or lake drainages, but places that would once have quietly sagged and formed a pond might now, under the right gas conditions, fail more violently. This is where scientific concern and public imagination diverge. On one side, you have sober worries: local safety, damage to infrastructure built on an assumption of stable frost, unexpected emissions of methane that complicate carbon budgets, the difficulty of working in terrain that might literally rearrange itself under your feet. On the other side, you have headlines about massive methane bombs waiting to shatter the planet, chain reactions of exploding tundra, runaway doomsday scenarios. The evidence so far doesn't support that second picture. The craters we've seen are dramatic but localized. They don't propagate like dominoes across the landscape. They're one of many ways permafrost can fail, and far from the most extensive. From a global climate perspective, they're probably a small fraction of total Arctic methane flux. But small fraction doesn't mean ignore it. For communities on the ground, for the engineers stringing pipelines across softening terrain, for the scientists tasked with making sense of a rapidly changing Arctic, these explosive features are real hazards and real clues. They're warning lights on the dashboard of a system we're still learning to read. And the fact that we can now watch some of them inflate and fail in almost real time tells us something important about the next part of this story: what these craters and the conditions that create them are revealing about the future of the Arctic and the rest of the planet. When you zoom out from the individual blowouts and look at a map, a pattern starts to emerge. These craters are not scattered randomly over the Arctic. They cluster in zones where 3 ingredients overlap: ice-rich permafrost, buried reservoirs of gas or organic-rich sediments, and rapid environmental change. In other words, they're popping up exactly where you'd expect a stressed system to show its first cracks. Permafrost has always been dynamic on geologic timescales. Ice wedges grow and decay. Lakes form, drain, and refreeze. Coasts slump into the sea. But for most of the Holocene, those processes have been paced by slow shifts in climate, marching forward over centuries or millennia. What's different now is the tempo. The Arctic is warming fast enough that landscapes are reorganizing within a single human career. A reindeer herder can remember when that valley was solid ground, when that low hill never wept water in late summer, when that riverbank didn't crumble like wet sugar. The Siberian blowout craters are extreme punctuation marks in that story. They're what happens when several lines of change cross at the same spot and the system can't adjust gradually. The ground doesn't just sag, it fails catastrophically. Scientists care about them partly because of the drama, but mostly because they expose the inner workings of the Arctic's frozen carbon vault. For tens of thousands of years, northern soils have been quietly stockpiling organic matter, roots, leaves, peat, animal remains, layer upon layer, locked away by cold. Add in thermogenic methane seeping up from deeper reservoirs, and you get an enormous store of carbon and gas held in place by ice and low temperatures. In most places, as permafrost warms, that carbon story is more slow motion than cinematic. Microbes wake up in thawed soil, chew through old plant material, and exhale carbon dioxide and methane. Pond bottoms bubble. Riverbanks ooze. The atmosphere feels those changes, but the ground surface doesn't explode. The blowout craters are the rare, violent version of that same basic process. They show that under certain conditions, thaw doesn't just mean a bit more soggy or slightly more greenhouse gas leaking out. It can mean pressure building in sealed pockets until the overlying ground can't hold, releasing a pulse of methane in seconds that would otherwise have seeped out over years. From a global climate perspective, the best estimates so far suggest these events are a minor piece of the Arctic emissions puzzle. They're visually spectacular, scientifically rich, but numerically small compared to the vast diffuse flux from wetlands, thaw slumps, and shallow continental shelves. But in climate science, small pieces matter, especially when they reveal hidden mechanisms. Every time a crater forms, it gives researchers a cross-section through frozen history. Layered ice, ancient soils, trapped gas, sometimes preserved plant material you can date and analyze. It's like someone dug a research borehole for you overnight, then scattered the contents across the tundra. Those snapshots help refine models of how permafrost stores carbon, how gases accumulate in specific stratigraphic traps, how heat and fluids move through the subsurface as the climate warms. When you're trying to predict how much carbon might leak out of high latitudes over the next century, those details matter. The craters also sit at the crossroads of different disciplines. For geologists, they're a new kind of surface process to classify and understand, something that looks a little like a volcanic maar, a little like a landslide scar, and a little like nothing we've catalogued before. For hazard forecasters and engineers, they're another reminder that what used to be stable ground is now conditionally stable at best. Infrastructure built on the assumption that permafrost is a permanent foundation is suddenly sitting on a material that can melt, flow, heave, and occasionally blow apart. For climate scientists, they're data points and warning signs. Small in immediate impact, but emblematic of a larger issue. Our planet's high-latitude systems are crossing thresholds faster than our models, or our monitoring networks were originally built to handle. And then there's the humbling part. These craters are forming in one of the least populated, most intensively mapped regions on Earth. Russia's gas heartland, crisscrossed by pipelines, watched by satellites, monitored by industry. And yet the first ones still took us by surprise. No one had a sensor in the right place at the right time. No one predicted, in a specific sense, this hill will explode next summer. If something this dramatic can happen unobserved, more subtle shifts almost certainly are. There are vast reaches of the Arctic, northern Siberia, the Canadian archipelago, interior Greenland, where we have only patchy data. a satellite pass every few days, a weather station here and there, the occasional field campaign. In between, the ground is changing largely unwitnessed. The blowout craters are stark reminders of the limits of what we know in remote, rapidly evolving environments. They expose how much of our understanding is still reverse engineered after the fact, pieced together from before and after images and a few hurried field seasons. And yet, precisely because they startled us, they've become symbols. A mysterious, smoking hole in the tundra makes for a visceral image in a way that a graph of permafrost temperature anomalies never will. It condenses a sprawling, abstract issue, carbon cycles, feedback loops, Arctic amplification, into something you can picture. The ground itself is restless. The frozen world is not as solid as we thought. It's easy to overinterpret that symbol, to leap straight to apocalyptic narratives about methane bombs and runaway tipping points. It's equally easy to dismiss it as an oddity and miss what it's trying to tell us. The more grounded interpretation lies somewhere in between. What the Siberian craters really reveal is not that the planet is about to literally explode under our feet, and not that everything is fine except for a few quirky holes in the ground. They reveal that as we push the climate system faster than it has moved in many thousands of years, we should expect surprises, new behaviours, rare events becoming less rare, edge case geology suddenly mattering to real people and real infrastructure. They reveal that the Arctic is not a distant, static backdrop, but an active participant in the planet's climate drama with its own sensitivities and thresholds. So, when we circle back to the question we started with, what's actually exploding out of the permafrost right now? The literal answer is simple enough. Pockets of methane-rich gas, water and soil driven upward by thaw and pressure. But wrapped around that literal answer is a larger one. What's erupting is also information about hidden carbon stores, about how ice and gas share the same underground spaces, about the ways a warming atmosphere can unsettle landscapes that once seemed immutable. It's a message carved into the tundra in letters hundreds of meters wide, telling us that the frozen ground we counted on is not just melting quietly. Sometimes it breaks. So where does that leave the mystery? Narrowed, but not closed. The most credible picture so far looks like this. In certain ice-rich hills and bluffs, thaw and groundwater movement allow methane-rich gas to collect in shallow pockets beneath a frozen cap. Seasonal warming, perhaps helped along by changes in snow cover, vegetation, or human disturbance, weakens that cap while gas keeps accumulating. Pressure rises until the overburden fails. In a few seconds, the system flips from locked to open, an explosion-like blowout, a jet of gas, ice and mud, and the sudden birth of a steep-walled crater that then slumps and fills with water. That story fits many of the observations, but not all of them, and not in enough detail. We still don't know exactly how common these conditions are, how big the gas reservoirs can get, or how quickly they recharge. We don't know why one hill vents harmlessly through cracks, while another waits, then fails catastrophically. We don't know whether a warmer, wetter Arctic will make these blowouts a little more frequent, or a lot. Those uncertainties matter, because they live at the intersection of climate risk, infrastructure safety, and our basic understanding of how frozen ground responds when you pull it out of the temperature range it evolved in. The craters are, in that sense, warnings as much as curiosities. They tell us that parts of the Arctic landscape aren't just softening, they're becoming capable of rare, sudden, violent change. If we pay attention, they can help us catch up to the pace of that change. If we don't, they'll keep arriving as surprises. If you found this deep dive useful, it really helps the channel if you like the video, subscribe, and share it with someone who still thinks permafrost is just solid ground. And I'd love to hear from you in the comments. Where in the world are you listening from? And what does climate change look like where you live?